Before I introduce today's speaker, just a reminder, our last speaker for the semester will be in 2 weeks, December 10th, and it'll be Ben Yang from GTRI. So it's a pleasure to welcome Sally Ng with us today. She got her bachelor's degree in chemical and environmental engineering from Hong Kong University of Science and Technology before getting her master's and PhD in chemical engineering at Caltech. She then did a postdoc at Aerodyne Research before coming to Georgia Tech about 8 or 9 years ago. She can't quite remember. It's been so long. Where she is currently an associate professor in chemical and biomolecular engineering with a joint appointment in earth and atmospheric sciences. She's one of the top 1% cited in the geosciences and is also an NSF Career Award recipient, but most recently was honored by Georgia Tech this past year for outstanding achievement in early career research. And so it is a pleasure to have her with us.
So thanks for the introduction and the opportunity to speak today, the pre-Thanksgiving seminar. So I was told I need to mention the word nano once, and I will. So today I'm going to tell you all about atmospheric aerosols, which are particles. And as you are sitting there, maybe eating a pizza and listening to me, you're breathing in these particles continuously. And they are very small nanoparticles, so you cannot see them. So this photo is taken from Stone Mountain and looking far away from, the background to look at Atlanta. And you can see an ocean of trees, and you can also see a haze. And there are plenty of organic particles in this photo. So what are aerosols? So people refer them to as particulate matter, or PM. You'll probably read about them in newspapers, or just aerosols, or atmospheric nanoparticles. So technically, aerosols is defined as a system of suspension of solid or liquid particles in the gas. But right now, it's mostly common use to refer to the particle component only. So when I mention aerosols, I'm talking about a suspended particle in the air. So when you think of aerosols, what are the pictures that might come to mind? So maybe you got a tailpipe emission, cooking. So this one is taken from the tech quad out there. So when the students are barbecuing, so these are cooking aerosols. Dust, wildfire emission aerosols, and volcano ash, and sea spray aerosols, and many others. And you can see them. Some of these are bigger than the others, so you can actually see that with your naked eyes. But many of the particles, like the particles in this room, they're too small, so you cannot actually see them. So when we think about these particles, what are the size range that we are thinking about? So this diagram shows the typical aerosol number and volume size distributions. So you can look at the scale is from 0.01 micrometer to about 10 micrometer. And this is the number distribution, this is the volume distribution. And because of the different emissions, chemistry, you end up with this natural distribution of aerosols. And you can group the aerosols depending on their size. So the ultrafine particle refers to the nanoparticles, which is less than 100 nanometers in diameter. And the fine particles are less than 2.5 micron. And the coarse particles are bigger than 2.5 micron. And when you read newspapers or articles about aerosols, you might come across these terms, PM1, PM2.5, and PM10. So this number signifies the size of the particles below that range. So PM2.5 correspond to these particles smaller than 2.5 micron in diameter. And PM2.5 is what EPA regulates. So EPA regulates PM2.5 mass for impacts on human health. So why do we care about aerosols? Why do I and many of my colleagues spend our lifetime studying these particles? Aerosols plays a very important role in climate and human health. And you could probably argue climate change and air quality are the two major environmental issues confronting each one of us every day. So this figure is from IPCC, which is the Intergovernmental Panel on Climate Change. And it shows the different radioactive forcing factors. You can see all these greenhouse gases. So the positive warms the Earth, negative cools the Earth. So I'm not going to go through each one of them, but I want to kind of draw your attention to the aerosol effect on climate. So how does a nanoparticle affect climate? An aerosol can absorb radiation and warms the Earth. An aerosol can also reflect radiation back to space and cools the Earth. What they do depends on what they are made of and their size. And aerosols also form the seed to make clouds. So with no aerosols, there will be no clouds. And clouds reflect radiation back to the space. And that also cools the Earth. So there are many different types of aerosols around the world, and each of them have very different chemical composition and properties. But overall, you can see that actually aerosols has a cooling effect. It helps actually mitigate the warming effect. But you can also see that there's a huge uncertainty bar. So that's why there are a lot more research that is needed to understand the aerosol impact on climate. And what about the health impacts? So according to this paper that was published last year, about 9 million people's death can be attributed to fine particle pollution. That is a staggering number. So I always refer to aerosols almost as a silent killer. You can think of other diseases and it sounds really scary, but when it is polluted outside, you won't immediately link that to death, but it is what these numbers shows. And this figure shows the global burden of disease, basically kind of what we die from. And you can think of the x-axis as the sum of mortality and morbidity. And you can go down the bar charts and find that air pollution is ranked really high in this global burden of disease. So the thing is that these particles are everywhere. You can't escape them, I guess, unless you go into a clean room. But even we are sitting here, we're breathing in all these particles. And so it is really important to try to understand how particle composition and properties are linked to their health impacts. And last but not least, aerosols also impact air quality and visibility. So this is a pair of pictures for Atlanta between a clear day and a hazy day. And I grew up in Hong Kong originally, and this is the Victoria Harbor. And you can also easily find a pair of photos between a clear day and a hazy day. And you can do this for every favorite cities that you like. And it's very easy to find this comparison. So today I'm going to focus on one particular type of aerosols called organic aerosols. And these pie charts corresponds to the submicron non-refractory PM composition around the world. So if you can see from where you are, you can pick your favorite cities. And the color of the pie chart corresponds to different composition of the aerosols. The green part of the pie is organic, so hence the organic aerosol. The red is sulfate, blue is nitrate, orange is ammonium. So you can think of submicron non-refractory aerosols are mainly made of these 4 to 5 different components. And their total concentration measured in microgram per cubic meter in the air varies from different places. And this is already data from more than a decade ago, and there are many more measurements around the world. But wherever you go, what we find is that organic aerosols is always one of the major components in these ambient particles. So just a little bit of introduction of where these particles come from. So you got different emissions, you got trees, cars, industry, and I have to act as fire because when I started giving this talk over a decade ago, there was not many fire emissions. But now, if you open up the newspaper, you will see that wildfire is becoming an important source of aerosols. So all these sources can emit particles directly. So if you are emitted as a particle, we call you primary particles because you're emitted as a particle. But however, these different sources can emit a lot of gas phase components. We call them volatile organic compounds. So remember, these are gas, not particles. But once these gases got emitted into the atmosphere, what happened to them? Atmosphere is really oxidizing. They're not going to stay as their parent compound very long. So what happened is that in the atmosphere, there are a lot of oxidants. So one of the major oxidants is this hydroxy radical, which is a very important oxidant during the day. Ozone is an important oxidant during the day and night. Nitrate radical is an important oxidant at night. So depending on when you are emitted, it might react in each one of these radicals. And once you react, you're going to form different products. So imagine you're compound A. Compound A reacts with different oxidants in the atmosphere, and eventually you're going to form a compound B. And maybe compound B has a much higher volatility, then you still stay in the gas phase. But what if compound B has a lower volatility? So thermodynamics require you to be in the particle phase because you are semi-volatile, you're non-volatile. So imagine if you're a gas phase compound and you want to be a particle, how can you be a particle? So if there are no particles around you, you are going to nucleate into a nanoparticle. So that is the birth of a new particle. But if there are many particles around you, the less energy method is to actually condense onto these existing particles. So this is the gas particle partitioning of these semi-volatile gas phase products onto existing particles to make a secondary organic aerosol. So primary aerosols are emitted directly as a particle. Secondary particles are formed in the atmosphere as a result of these very complex chemistry. And if you look around the world, most of the aerosols are actually secondary. Unfortunately, they are complex and not as easy as just directly emitted. And once these particles are formed, that's not the end of the world. Like aerosols generally live for about 7 days to 10 days in the world, so they can undergo many different chemistry. Gas phase aging, heterogeneous phase aging, or multi-phase aging. So all this will continue to change the properties and composition of aerosols, impacting their impacts on climate and health. So we're going to focus a lot on these biogenic VOCs today. So these are VOCs emitted by vegetation, mostly from trees. So if you go to a forest, you smell nice forest smell, chances are you're smelling some of these compounds. So the smallest and simplest one is isoprene, which is a C5 compound. And you've got monoterpenes, which is C10 compound, sesquiterpenes, which are C15 compounds. And so these are always emitted by vegetations throughout different times of the year. And when they get emitted, they can be reacted with those oxidants, like ozone, hydroxy radical, or nitrate radical, depending on whether it's day or night. So in my group, we take this systematic approach to understand how aerosols are formed and what are they made of. So we have laboratory studies, which I'll show a video and a diagram of it. So this is basically a batch reactor. It's an atmospheric simulator that allows us to look at the kinetics and mechanisms of aerosol formation. We also do a lot of ambient measurements. So sometimes we take all the instruments to the field and do measurements at that particular city or location to try to understand aerosol formation in the ambient. And the tools that we use in my group are mostly mass spectrometers. So we have mass spectrometers to look at the gas phase composition and aerosol phase composition and kind of try to piece together the pictures of how these aerosols are being formed. So I'll give you a quick rundown of some of the current projects that we have. So this is what I'm going to spend my time mostly today, is talk about how emissions from human activities can affect how the emissions from trees in their making aerosols process. And we also have some projects to look at aerosol formation from wildfires and biomass burning. As I mentioned, this is increasingly becoming an important source of ambient aerosols. We also have some projects on aerosol health effects. I might or might not have time to go through that at the end of the talk, but we'll see. And we also do instrument development. So I worked at an instrument company before I started at Georgia Tech, so I still have a number of collaborations with them. So let's think about what happens when things get emitted. So this is kind of the beginning of our stories today. So you have all these different sources. You've got power plants emitting sulfur dioxide. You've got cars, vehicles emitting nitrogen oxides, and livestock emitting ammonia. So all these get emitted into the atmosphere. They might form these inorganic aerosols, sulfate, nitrate, and ammonia. But remember, today we're going to talk about organic aerosols. So once these different sources get emitted, they will interact with these emissions from trees because they are all in the same vicinity of each other. So you got the isoprene, you got the monoterpene. So that's why today I'm going to tell you how these emissions from human activities interact with these emissions from trees and affect how these tree emissions form aerosol. So this anthropogenic biogenic story started over a decade ago. So it actually started in the Southeast US. If we remember the photo I showed at the beginning of my talk, we are in a city bathing in an ocean of trees. So the Southeast US is actually the most ideal place in the country to study this interaction. So over a decade ago, one of my colleagues, Rodney Weber, he did some measurements here in Atlanta. And he found that a lot of the organic aerosols or organic carbon is actually biogenic, so it's from trees. But at the same time, this aerosol has a nice correlation with carbon monoxide. Carbon monoxide is a tracer for anthropogenic pollutant. So then you start scratching your head. You're like, why are the emissions and aerosols from trees have anything to do with human activities? What is their interaction? So the hypothesis is that these aerosols probably start their life from some sort of trees, but somehow there's a mediation from anthropogenic sources. The question is, what is the mechanism of this interaction between this anthropogenic and biogenic reactions? So we start addressing to this question by going around sampling in the Southeast US. As I mentioned, this is one of the best place to actually address this scientific question. So in 2013, there's a huge ambient measurement study called SOAS, and it takes place in Centerville in Alabama. So my whole group moved there for a month and a half with many other researchers from around the world and country. This is like a $40 million measurement funded by multiple agencies. So it is in the middle of a forest. So we sample there for a month and a half. We also do a post-SOAS measurement. And at that time, we also have an EPA health center between Georgia Tech and Emory University to look at air quality and health effects. So we also do a lot of measurements in different places in Atlanta. So I came from the Ford ES&T building, so on top of that building, we also have a sampling site, and there's a roadside site that's next to the 75 and 85 highway, and there's also a sampling site at Jefferson Street, which is just about 10 minutes west of the campus. So the instrument that we carry or move to all these sampling sites is called the aerosol mass spectrometer. This is kind of like a workhorse of our lab. So you can see the puff of aerosol go through this aerodynamic lens. It goes through a chopper, and if you have good eyes, you can see that the little particle fly faster, right? So this is a time of flight, so you can actually get some size information. And once it hit this, it evaporates at 600 degrees Celsius, and it was analyzed by the mass spectrometer. So this instrument allows you to get a continuous measurement of submicron non-refractory species, organics, sulfate, nitrate, ammonium, and chloride. So the color is the first thing I learned once I learned about this instrument. So organics is always green. So we take this instrument around different places that I mentioned earlier to do the measurement. And the top part of the pie are from summer data. The bottom part of the pie are from winter data. But you can see that no matter whether it's summer or winter, you can actually see that the green part of the pie is always very large. The green part of the pie is organic aerosol. And you can pick your favorite places. Georgia Tech campus, we have a lot of organic aerosol also. The question is, what are these organic aerosol? When I say sulfate aerosol, it's just made of sulfate. When I say organic aerosol, what do I actually mean? Organic aerosols are actually made up of hundreds, thousands, and many thousands of different components. It is very difficult and challenging, and at this moment, we cannot even understand every single component of this organic aerosol mixture. So what kind of data do we get? I thought I'll show this slide. So this is one of the slides I show my undergrads, during my class. So using the aerosol mass spectrometer, you get the time series of different components. You see the organic going up and down, nitrate, sulfate. You've got the composition, so this is a mass spectra, and you've got size resolved information. So you can see that most of these particles are nanoparticles, and they're less than 1 micron in diameter. So you might raise your hand and ask, just like, Sally, what are these big peaks? And I always encourage my undergrads to guess. And after a couple of questions, they will always get to the right answer. So this is right next to the marquee site and right next to our football stadium. So if I go and look at the football schedule, these are actually the days when we have a football game. And the aerosols increases during the football game time because of tailgate parties and because of cooking aerosols. So actually, if I don't look at the football schedule by looking at my own data, I can actually give you the football schedule. So this is always, the slide I try to get the undergrads interested in this research. So the question is that this mass spectra measures all the organic aerosols, but because it uses electron impact, so a lot of these components get fragmented, and we lost information of what they are. Are they alcohols? Are they carbonyls? Are they carboxylic acids? So how do we actually look from all these fragments and try to get a sense of what are the source of these aerosols? So to do that, we turn to a mathematical tool called the positive matrix factorization. Basically, you take the instrument and you do measurements. So this is like a mass spectra. You acquire mass spectra every 5 minutes. So after a long time, you got this gigantic matrix. And with PMF, you can actually get different factors. And these factors can be different sources of aerosol. And each factor has their unique time series and unique mass spectra. So based on the mass spectral features, correlation with external factors, diurnal trends, residuals, we can actually get different types of aerosol. That's why I got the cooking aerosol. So you can see the cooking aerosol is one type of aerosol, and the cooking aerosol actually a very nice diurnal cycle. It always peaks at lunchtime and dinner time, so it's pretty clear. And the biomass burning aerosol has its own signatures. Hydrocarbon-like aerosol is mostly from combustion, primary particles. And then we got these different types of SOA, which is, remember, SOA are the particles that are not emitted as particles, but they are from the chemistry in the atmosphere. So today we're going to focus on some of these SOA. So I'm going to tell you two types of SOA. The first type is the isoprene SOA. Remember, isoprene is the C5 compound that is emitted, from trees. And remember, these are summer data and these are winter data. So the first thing you notice is that isoprene OA is the blue, and there's no isoprene OA in winter, because the trees, they do not emit isoprene in winter, so this makes sense. And isoprene OA is actually a major component in summer. It's about 20 to 40%. And when we look at the time series, remember the blue here is the isoprene OA, the red is the sulfate. Where isoprene comes from? Isoprene comes from trees. Where does sulfate comes from? Sulfate comes from sulfur dioxide. Where does sulfur dioxide come from? From power plants. So why do aerosol form from trees? Has anything to do with power plant emissions? That is the question we set out to answer. What is the role of sulfate and anthropogenic human activity pollutant affect the emission and formation of aerosols from isoprene, which is from trees. So think about sulfate aerosol. If you have a particle and you have sulfate inside this particle, sulfate loves water. So sulfate can take up water vapor in the ambient and make the particle more aqueous. Sulfate, and in this case, it will increase the volume and the surface area of that nanoparticle. And sulfate is a major source of atmospheric acidity. So when you have more sulfate, you can also have highly more acidic aerosol, and that can affect the chemistry in these particles. So we are interested in seeing how particle pH, particle water, and sulfate affect isoprene aerosol formation. So in this figure, the y-axis is the acidity, H+, and the x-axis is the water. And this different grid is just sulfate with different concentrations. And the size of this different dot is the amount of isoprene SOA. So that's a lot of information, so let's just focus on this plot here. The y-axis is the acidity, x-axis is the water, the size of the particles, the size of the data points are the isoprene aerosol. So you don't really see much trend here. It seems that the dots are pretty much the same size, no matter what pH and particle water is. So it seems that the pH and particle water are not controlling or mediating isoprene aerosol formation. But if you look at this direction, you can obviously see that the size of the data point are getting bigger, right? So the size of the data point refer to isoprene aerosol. They're getting bigger because sulfate is increasing. So it shows that sulfate actually has a direct role in controlling how much isoprene SOA is being made. And isoprene OA is formed from this pretty complex chemistry, but it involves two different steps. First, you need to form this product, intermediate product, and it needs to be uptake onto the particles, and then you got the aqueous phase reaction. And you can actually parameterize this with a heterogeneous reaction parameterization model in which you can look at the uptake coefficient and surface accommodation coefficients. So we don't have enough time to go through all the details, but what we learned is that sulfate actually enhanced isoprene aerosol formation by doing two different things. It increased the surface area and volume of the particle, so it enhanced the uptake of these intermediate products onto the particle, and then it also enhanced the aqueous phase reaction in these particles. So sulfate from power plants, isoprene from trees. So what we show here is that over the last several decades, the good news is that the aerosol concentration in this region is going down. So you can see that it's been constantly decreasing with sulfate and organic carbon. So now you learn that there is a mechanism for sulfate to influence aerosol formation from trees. So this is very good news because sulfate has been decreasing in the Southeast US due to tighter pollution control. So that means as sulfate goes down, the amount of isoprene aerosol is going to go down. So this is really a win-win situation in terms of pollution control, is that you reduce the sulfate aerosol from power plants. At the same time, this also reduced the aerosol formed from trees. And that's why total, as a reduction of aerosols, you got twice the impact by just reducing sulfate aerosols. So that's the story of sulfate. So now let's move on to look at the story of nitrate, or NOx. So now let's change gears and look at this light blue part of the pie, the light blue part of the pie. And so one of the first difference, not light blue, it's light green part of the pie. One of the first difference between the light green and the blue is that the blue is only on the top pie charts, right? Because those are summer data. But the light green is everywhere, even in winter. So when my colleagues from the Northeast look at these data, they're like, winter is just snow. But I was like, then you gotta come to the Southeast US in winter. We still have a lot of trees here, right? So the LOA actually accounts for quite a large fraction of the aerosols in the Southeast US. So this is a time series or temporal variation of the LOA. This is midnight. You can see that it peaks at night. So when you think of aerosol formation, a lot of the time people think of photochemistry is very strong during the day right now, right? So you think of aerosol formation during the day. Why does it peak at night? And then you look at isoprene. Isoprene peaks during the day, so maybe they have nothing to do with each other. But then you look closer, you find a bunch of compounds that also peak at night. And remember, these are monoterpenes. These are the C10 compounds that I showed you at the beginning of the talk. These are also from trees. So the question is that maybe these compounds are reacting with something at night to make aerosol. And one of the most important radical at night is the nitrate radical, which is a product of NOx and ozone. So this is where your NOx can potentially interact, so NOx is from cars, can potentially interact with these emissions from trees to change how aerosol is formed. So one thing we learned is that the LOA actually correlate really well with organic nitrate. So what is an organic nitrate? Organic nitrate is a compound with an ONO2, like a nitrate group attached to it. So the question is why they are related. Because perhaps this chemistry forms a lot of nitrate aerosols. And then the question is this like something strange or unique about the Southeast US? And we decided to do a meta-analysis of all the data sets in the world. And so now all these pie charts, the whole pie chart is the organic aerosol. The blue part of the pie is nitrate, organic nitrate. And you can see that it's not just in the Southeast US, but everywhere around the world, organic nitrates is a very important part of the organic aerosols. And in some places in Europe, it can even account for 80% of the total aerosols. So with all these ambient observations, we're like, what do we do now? We go back to the lab, actually, to try to understand how this chemistry can actually make organic aerosols and organic nitrate. So this is a schematic of the Georgia Tech Environmental Chamber facility. It's about 13 cubic meters chamber. So these are atmospheric simulators. So the chamber is surrounded by multiple UV lights, hundreds of UV lights. It's temperature controlled between 4 to 40 degrees Celsius. So you can simulate any atmospheric environment in this facility. And surrounding the facility, we have a suite of analytical instruments to make the gas and aerosol composition. So I'm not going to go over all this, but suffice to say that we can measure aerosol number, concentration, mass concentration, volume concentration, gas phase, and then particle phase composition. So all these instruments are real time. So basically it pulls the sample or the nanoparticles from the chamber, and you can actually directly see this in your mass spectrometer. So the first experiments that we do is the alpha pinene and beta pinene. These are the monoterpenes, and we put in the nitrate radical. And you can immediately see there's no aerosol. And once we add in the oxidant, there's a lot of aerosol being formed. And these two compounds are very similar in their structure, but they have very different potential in terms of their aerosol formation. And this is just a proof of concept that we are making aerosols in these reactors. And recently, with the NSF MRI proposal, we also acquired this quite a mouthful instrument, figural high resolution time of flight sims. But just to say that, this instrument allows you to look at the gas phase composition and the aerosol composition at the molecular level simultaneously. I always say that you are what you eat. So when you look at an aerosol, you're not just looking at where the aerosol come from. A lot of the aerosols, remember, mostly come from the gas phase oxidation. So this instrument allows us to look at that gas particle equilibrium and partition in real time. It's a very powerful instrument. So we measure a lot of different organic nitrates in these experiments. You can continue to look into that. The list can keep going and going. So the take-home message is that when we do these experiments in the chamber, we see a lot of potentially relevant compounds forming in a chamber compared to the ambient environment. So why do we care about organic nitrate? Carbon and nitrogen cycles are the two most important cycles in the world. So ozone, we'll start with NOx. NOx cycling between NO and NO2 makes ozone. Remember, ozone is a secondary pollutant. There's no source of ozone. Ozone is made in the atmosphere. And ozone and NO2 can make nitrate radical. And we're not going to talk about this process, but eventually all these oxidation processes can make organic nitrate. So this is the formula for organic nitrate. It's a group and ONO2. So what happened to the organic nitrate? Now this circle here is an aerosol. Some organic nitrates are low volatility enough that they don't want to be exclusively in the gas phase. So they want to be in the particle phase. The question is that right now this process is really not well constrained. How much does this contribute to the aerosol formation? And when this nitrogen is trapped as organic nitrate, is this just stay there or it come back out? So remember now the cycle effectively take the nitrogen from the NOx and trap as organic nitrate and trap it in the particle. And this is going to interrupt the ozone formation. So that's why this NOx cycle and organic nitrate can play a potential role in aerosol formation and ozone formation. The problem is that what happened to this nitrate after they go into the particle? Remember, aerosols live in this world for about 10 days, right? Do they stay as organic nitrate? Or sometimes they go from different places and they will evaporate and partition back. Or they can undergo hydrolysis and make nitric acid. Nitric acid comes back and come back to nitrogen. Or they can undergo photolysis and return this nitrogen from here to back there. And now ozone cycle starts again. So all these are very complex nonlinear processes in the atmosphere. And we are interested in doing experiments in the lab to constrain each of these different processes. And today we're just going to focus on one of them for the interest of time, is the hydrolysis. So I'm sure that none of you, I haven't seen familiar places in my research group, so I'm sure none of you have run a chamber experiment before in your life. So what do you do when you do a chamber experiment? So you go to the lab, there's your Teflon big reactor, you put in some seed particles, ammonium sulfate, right? These are inorganic particles. And you can design experiments so that these particles have different water. We're going to study hydrolysis. So the way to study hydrolysis in these suspended particles is to create particles with different amount of water, right? So you can use this experimental matrix to make particles of different water. And you can add your VOCs, and you can add your oxidants, and you can turn on your UV light. And you're going to make organic aerosol, which is green. Okay, so this is a batch reactor, pretty much, that allows you to simulate this whole process of making aerosols. So we're just going to look at two examples from alpha-pinene. Alpha-pinene is the most abundant monoterpene in the world. So the top part is the daytime chemistry. Remember, atmospheric chemistry does not sleep at night. The top part is the daytime chemistry. The bottom part is the nighttime chemistry. And this is a mass spectra. So it's a lot of information, but I'll walk you through. Let's just take a look at this top. So here is the CHON fragments. So anything on the top panel here are organic nitrate fragments. Here are the CHO fragments, and these compounds do not have nitrogen, so these are non-nitrate organics. So if you compare this figure and that figure, you see that there are a lot more CHON states here than there, right? And this is not surprising, because this is an experiment that is done with nitrate radical. Nitrate radical itself has a nitrogen, so it just attached to the alpha-pinene and make all these organic nitrate products. So the one take-home message from here is that nighttime chemistry is more efficient than making organic nitrates than daytime chemistry. And the same story goes for beta-pinene. So when we do these experiments, it runs for several hours. And we can actually see the organic aerosol, which is non-nitrate organic, and the organic nitrates increase pretty quickly. And you can see the rate of increase of these aerosols are very different, much faster here, much slower here. It's just that this alpha-pinene and nitrate radicals react much faster. And the same story for alpha-pinene and beta-pinene. And this is good news, because if you are an atmospheric modeler, you don't want to run a simulation for different types of compounds if they are so different. So it is really good news that alpha-pinene and beta-pinene, which are both monoterpenes, actually have very similar behavior. So remember, the story I'm going to tell you is about hydrolysis. How does organic nitrate in the particle can potentially become nitric acid and go back to the gas phase? So when you look at hydrolysis, if there is hydrolysis, if you look at this ratio, what would happen to this ratio if there is hydrolysis? This ratio will decrease, because organic nitrate is just going to hydrolyze away and become nitric acid. So this ratio should decrease if there is hydrolysis. So now we're going to look at our data and see if this is true. So this is the alpha-pinene OH. This is the alpha-pinene NO3. And let's take a look at this top. So the red ones are the dry experiments. So you can think of the dry experiments, there should be no particle water, right? So there should be no hydrolysis. So this is what it is. But the purple and the blue ones are the experiments where we're done with particle water. And you can see that this ratio is lower, right? Remember our hypothesis in the previous slide. If this ratio is lower, then there is hydrolysis. So this seems to fit that picture. And you can see that the nitrates formed from this, the difference is smaller. So it seems that there are more organic nitrates formed in this system that will undergo hydrolysis. But you did not see that slow decrease. If hydrolysis is a very small, slow process in these particles, you will see this ratio slowly decreases. But there's no slow decrease here, it just kind of stabilizes. So what this shows is that it seems that the hydrolysis happened very quickly in these nanoparticles. And many studies in the past have done studies in a bulk, in a jar. And this is the first time that we systematically look at this in suspended nanoparticles. And again, the story is very similar for beta-pinene. But maybe you should not take my words for it. Remember I told you, if this ratio decreases, that means there's hydrolysis. But you can raise your hand and ask, what if this number or this amount does not decrease, but the organic aerosol increase? So this ratio can also decrease. So maybe you're not interpreting your data correctly. So we address this by looking at the mass spectra. So now this is a different spectra between the dry and humid experiments. And we confirm that this ratio indeed decreases because organic nitrate is decreasing and hydrolyzing, not because the organic aerosol increases. So this is an important way, when you guys do experiments, you get your data, it's just really important to look into alternative explanations and make sure that you kind of discount those alternative explanations. So as I mentioned, in the past, there are many studies in bulk, jars, and this is the first time we did a systematic study on suspended aerosols. And we obtain these lifetimes and these fractions of organic nitrate that can be hydrolyzed. And you can ask, what do we do now? So we're collaborating with modelers. Now this really provides the fundamental data for them to constrain this organic nitrate formation, nitrogen cycle, ozone formation, and aerosol formation in their models to see how aerosols can actually, how these processes can actually impact all these processes in the atmosphere. And these observations are actually completely consistent, so I thought I would show at least a chemical mechanism, right? So this is alpha-pinene, and this is the daytime oxidation, this is the nighttime oxidation. This is just to show you, even though you have the same compound, if you encounter different oxidants during the day and night, you form very different types of organic nitrates. You'll form a tertiary organic nitrate here, and you'll form a secondary organic nitrate here. And they have very different lifetimes and tendency to hydrolyze. So our observations in the lab are very consistent with the proposed chemical mechanism. So I'll quickly wrap up this part. I don't know what's the time. Yep, so maybe we have a few minutes for the health effects. So basically, the two stories I told you today here is between trees and human activities. The first compound emitted by trees is the isoprene, the C5 compound. The story I told you is that the isoprene aerosol formed from trees, to a large extent, is controlled by sulfur dioxide and sulfate from power plants. The second story is the monoterpene, which are the C10 compounds emitted by trees. And this has a lot to do with NOx. NOx main emitter is from cars and vehicles. So that is the story of how emissions from your car when you're driving affect the aerosol formation from trees. We also look at the daytime and nighttime oxidation, and we look at these different organic nitrates and how much they hydrolyze and can recycle that nitrogen from the organic nitrate back to NO and NO2 in the gas phase. So when we put all this together, we can find that NOx from car emissions, sulfur dioxide from power plants, together can actually potentially control about 40 to 70% of the total organic aerosols here in the Southeast US. That is a huge number. So that means whenever we're doing, if you take one thing away from this seminar, is that all the human activities that we're doing, in our everyday life actually plays a role in all this chemistry in the atmosphere. And this controls the amount of aerosol formed from trees. And we love trees, we don't want to cut them down. But this is actually good news because by controlling these anthropogenic pollutants, we can actually reduce the amount of aerosol, formed from the trees. So I will thank my group and the funding agencies and all the collaborators here, but I have a few minutes and I'll kind of give you maybe a teaser on the health effects work that we're doing. So this is all chemistry, right? So when I started at Georgia Tech about 8 years ago, I was like, remember my introduction slide? The two major reasons for studying aerosols is climate and health, right? So how do we potentially link all this complex chemistry to their health impacts? So we got a grant from the Health Effects Institute to look at aerosol impacts on health. So many toxicology studies have suggested that the aerosol-induced oxidant production is a possible mechanism for health effects. So you would generate these reactive oxygen species when you are exposed to these particles, and they can do many different bad things if you accumulate many of these reactive oxygen species in your body. So we use two different types of assays to evaluate what is the oxidative potential and reactive oxygen species generation capacity of these different aerosols. So this is a chemical assay which is developed mostly by my colleague Ronnie Weber in EAS. So this is a chemical assay. You can think of this chemical assay as measuring the redox active species in the PM samples, in the aerosol samples. So the more it is, then the higher the oxidative potential, there are more oxidative species in this suspended aerosol. And my group, we developed a cellular assay in collaboration with Julie Champion, my colleague in CHBE, to look at how much ROS, reactive oxygen species, and how much reactive nitrogen species is formed when we expose these cells to aerosols. And the cells that we use are macrophage cells and also the cardiomyocytes. And like my last class in biology was probably in college. That's a long time ago. And I look always much younger than my age. So in order to start this work, I pretend to be an undergrad and sit in some biology classes. And it was really fun. So of course, I told the professor ahead of time, but nobody in my class knew that I was a professor. So for these studies, we started our experiments with different VOCs. So by now, hopefully you recognize isoprene and alpha-pinene. This is a sesquiterpene. So these are all from trees. But actually, I can have another seminar on aerosol formation from anthropogenic pollutants. So all these alkanes and aromatics are also emitted, from our human activities. So the goal of this project is to really try to see, can we get a better understanding of how the different type of aerosols form, how toxic they are. Hopefully the tree aerosols are not killing us, right? So that's kind of what we did. So we used this DTT assay. Remember, this kind of signifies how much redox active species are these particles. And these are just the shorthand of these compounds. So isoprene, alpha-pinene, this is what the story of the day. Isoprene, alpha-pinene, they're pretty low, so that is good. What is the highest? The highest is naphthalene, which is a 2-ring compound. So what this is showing is that these different VOCs, even they react in the same way, they make products of different toxicity. So the compounds that started with multiple rings, or the polyaromatic hydrocarbons, are the most toxic, at least based on this particular assay. So that is chemical assay, but now we have a cellular assay, and we also measure the different cytokines. And what we learned is that we can really now starting to link the composition of these aerosols, the mechanism of aerosol formation to their health impacts. And one thing that is kind of not a very good news is that you can think of this as toxicity, the ROS generated by cells, and this is kind of the oxidation state, which you can think of as the lifetime of aerosol. So remember, aerosols live in the world for 7 days or 10 days. This is a quiz, one of the exams for my undergrads, right? So during those 10 days, aerosols continue to age because of all the chemistry that I talk about. And what you can see is that based on this measurement that we do, it seems that as aerosols continue to age in the atmosphere, they can become actually potentially more toxic. So this is actually one of the first studies, and more studies need to be conducted to understand this trend. And if this is actually true for all different type of aerosols. And that's pretty much all I have today, and I want to show you a video. So our lab was featured in ESPN, I think 2 years ago. So we were playing Clemson in the football game. So Georgia Tech playing Clemson. Unfortunately, we lost badly in the football game, but my group were very happy because we got featured on TV. So hopefully this plays well and we can see.
ESPN College Football, brought to you by Dr. Pepper. It's a college football tradition. At the redesigned 2017 Kia Forte.
Well, I don't have to tell Jesse, but at this great academic school over the engineering department, a lab, they recreating UV lights from the sun to study air pollution, smog, its effects on human health and the environment. What is your main?
So that's all I have today. I'll thank you for your attention, and I'll take any questions.
So you talked about how reducing human pollution,
Yep,
like sulfate
yep.
and nitrate, causes also a decrease in these organic aerosols. So presumably the tree emissions, the isoprene and the terpenes are not decreasing unless we cut down the trees. But presumably they stay the same. So what is the fate of those volatile organic chemicals in the absence of the aerosol formation?
Yeah, so that is a really good question. So basically what happened is that when you react all these VOCs, in the presence of NOx, it will undergo one pathway. So the first pathway is that you make an LQ radical, R dot, and R dot become a peroxy radical, RO2 dot. So what happened to RO2 dot in the atmosphere? When you have NOx, RO2 dot react with nitrogen oxide. When the NOx keep going down, RO2 dot will react with other radicals. It can react with HO2, or it can undergo unimolecular isomerization by reacting with itself. So basically what happened is that when the NOx is going away, then it's going to change the pathway of this RO2 dot react, and you're going to make a different types of compounds and with different properties and impacts. Yeah, so that is like a research question actually, is that how the decreasing emissions affects the aerosol formation from these vegetation emissions. Yep.
What was the mode of uptake of the sulfates? How do they absorb to the ground?
So sulfate dioxide get oxidized and eventually make sulfuric acid. So sulfuric acid is really, it loves water. So it essentially being in a particle in terms of the sulfuric acid. So that's kind of where most of the atmospheric sulfate comes from. It started its life as sulfur dioxide emissions from the power plants and get oxidized in the atmosphere by hydroxy radical, the OH. And that's pretty much the basis of all these inorganic particles that we are seeing in the ambient. And if you go to Europe, there will be fewer sulfate particles because they get rid of all the coal-fired power plants. And if you go to the West Coast compared to the East Coast, because we have more power plants here, so they also have lower sulfate aerosols.
That basically goes to the roots and then plants uptake that.
Yep, so not plants uptake. So if you have a sulfate particle, right, and I have a tree, isoprene, like emitting isoprene, right, and isoprene is going to form this compound, like an intermediate product, and it's going to be uptake to the sulfate particle. And that's not the end of the story. Once this compound goes to the sulfate particle, there are particle phase chemistry that can happen. So this is kind of how it interacts, because sulfate, remember, sulfate loves water. And this compound that is made from trees loves water. Yep, exactly. So sulfate makes the particle aqueous, right? So now you got sulfate, first of all. Maybe you don't have that much water. And then later, sulfate loves water, so sulfate is going to make an aqueous particle. So instead of a dry particle, you got an aqueous particle hanging out here. And this product from isoprene loves water. When it sees the aqueous particle with the sulfate in there, it goes and got taken up onto that particle. And it started with all the interaction right there.
I guess I'm trying to understand, like you mentioned that if there is more sulfate produced by the compound,
Yep.
the plants also produce.
The plants don't produce. It's just that the compound, the plants do not produce more. The plants go and produce whatever they do. It's just that more uptake. So imagine if you have 10 units of these compounds produced by the plant, by trees, 10 units, right? And if you have more sulfate, more of these 10 units is going to be taken up by the sulfate particles, right? So if you reduce the sulfate, then maybe only one would be taken up. So there will be less interaction and less aerosol being formed. So the sulfate does not affect how much the trees emit. It affects how much of those products get taken up to the particle. Does that make sense? Yeah.
Actually, we are talking about outdoor aerosols, like, but nowadays, like in the past few years, like the VOCs have increased in indoor environment. So is there any chance that organic aerosols can be formed from the VOC?
Yes, that's a wonderful question too. So yes, we have VOCs in this room. And if you're sitting next to the window, what do you have? You have sunlight. You might have hydroxyl radical. So actually, you are doing chemistry right there also. So if you use cleaning product at home, like something that smells like lime, lemon smell, that is actually a compound called limonene. Limonene is a monoterpene. So I try not to do cleaning at home with limonene near the window, because what happens is that you're making organic aerosol from the chemistry that I talk about in your home, right? You're spraying limonene, cleaning your surfaces. Limonene evaporates as a gas phase compound. It reacts with ozone or hydroxyl radical near a window and make organic aerosol. And where did that go? It goes in your body, right? So the indoor chemistry is also as interesting as outdoor. And there's a lot of interest in our community in terms of looking at how the VOC emitted in indoor. What type of VOC emitted? Are they the same or different from different cooking activities or just different activities in homes? And what are the oxidation chemistry? What are the composition of the aerosols? The one thing in the indoor is that we have ventilation. So a lot of these particles, depending on how strong the ventilation is, could just be ventilated out. But yes, the indoor chemistry is also very interesting and complex.
You did mention that the public show that the population intensity, how would that affect the whole situation?
The population density, or the human population. Yeah, so I guess like with more people, then you have more activity. So one thing that I can link to the population is actually ammonia. So today I talk about the story of the monoterpenes and isoprene with nitrogen oxide and sulfur dioxide. So if you look at the trends in the US and even in Asia, China, the sulfur dioxide is going down, nitrogen oxide is going down. So one of the things that is actually increasing is ammonia because of the food demand. When you have more people, you need more food, right? So the use of ammonia, the fertilizers, then the ammonia concentration is actually increasing. So one of the research questions is that in a future world, when the pollution control is getting better and better, you have nitrogen oxide decreasing, you have sulfur dioxide decreasing, but you have ammonia increasing. How would that affect all this chemistry that I talk about today? So that is, a good question to address.
One more question? If not, let's make Sally one more time.
Thank you.